regeneration in any cycle means transfer of heat within the cycle from higher temperature to the lower temperature. First of all, let us study about what is ideal regenerative Rankine cycle. In this cycle, the steam is entering the turbine from the boiler. It is expanding, doing work, and the exhaust steam leaving the turbine are condensing in the condenser, and we get a condensate liquid at the end of the condenser. This condensate liquid leaving the condenser is passing through the casing of the turbine, where it is heated. Heat transfer. It is heated reversibly from the steam to the condensate liquid. The condensate liquid leaving the condenser is heated reversibly with the delta T tends to 0 between the steam, expanding steam in the turbine, and the condensate liquid. The condensate liquid leaving the turbine casing now is at a saturated liquid state, which is entering after pumping into the boiler. So the cycle could be indicated on the TS plane. Of course, pump also you could keep the pump before the casing also sometimes. The steam is transferring heat, neglecting the pumping, which is very shown as a small vertical line here. The heat loss from the steam to the feed water can be seen as a decrease in entropy. The increase in entropy of water is shown by delta S of the water. The decrease in entropy of the steam is shown by delta S of the steam. Therefore, it is only a distorted vision of the reversible Carnot cycle, a rectangle on a TS plane. So, in the ideal regenerative cycle, it is assumed that the steam is heating the water, feed water. The delta S of the water shall be taken as delta S of the steam. This is plus, this is minus. If heat transfer occurs reversibly with delta T tends to 0 between them, that is an ideal regeneration, then delta S of the universe is equal to 0. No entropy generated during this heat transfer. So external heat transfer is there only in the heat supply, that is in the process A to B, and the heat rejection process will be there only in the C to D as such during the condensation at constant temperature, because both heat supply and Q are occurring at constant temperature. This ideal regenerative Rankine cycle can be considered as a reversible cycle. Therefore, thermal efficiency of ideal regenerative Rankine cycle shall be equal to the thermal efficiency of Carnot cycle. So, in the ideal regenerative cycle, it is assumed that the condensate liquid leaving the condenser is heated by the steam expanding in the turbine reversibly with delta T tends to 0. But such heat transfer is practically feasible? No. The practically not feasible it is, because when the steam is transferring heat to the water, it becomes too wet, dryness fraction greatly decreases, and such wet steam is not compatible to expand in the turbine because it will cause the turbine blade erosion. So, ideal regenerative cycle is only an imagination whose efficiency will be equal to that of Carnot cycle. Let us see now the actual regenerative Rankine cycle or practical regenerative Rankine cycle. The flow diagram can be seen as the high pressure, high temperature steam generated in the boiler enters the turbine. High pressure, high temperature, superheated steam leaving the boiler enters the turbine, where after certain expansion of the steam, the steam is bled. Live steam is bled. Live steam is bled from the turbine, and the remaining steam expands in the turbine doing work, and then this steam enters the condenser, where it rejects heat to the cooling water, condensing into feed water. It is pumped there to the bleeding pressure. Now this liquid condensate leaving the condenser and pump now enters the feed water heater. The live steam bled is mixed directly with the water, condensate water in the feed water heater. The liquid condensate gets heated up because of the latent heat of condensation of the steam liberated from the bleeding steam. The cycle can be seen on the temperature entropy diagram. One, two, three, four, five, six, 7. State 1 is the state of the steam entering the turbine. State 2 is the state of the bled steam. This is called bleeding steam. Bleeding steam or live steam, which is trapped from the turbine while it is expanding, is at state 2. Live steam means having a considerable enthalpy. The remaining steam expands from 2 to 3 isoentropically, which then enters the condenser, where it condenses into saturated liquid and then pumped to the bleeding pressure in the process 4 to 5. This condensate water at state 5 now enters the feed water, which is heated in the 5 to 6 process due to the latent heat of condensation of the live steam is liberated. So, finally the state of the saturated liquid leaving is at state 6. The state of the liquid water is saturated liquid at state 6, corresponding to the bleeding pressure. This water is pumped from bleeding pressure to the boiler pressure. So, totally there are 3 pressures, that is boiler pressure, that is P1, bleeding pressure, BLP indicated, another is condensing pressure. There are 3 pressures totally in the cycle. This is called practical or actual regenerative Rankine cycle. Now, I suppose 1 kg of steam is entering the turbine from boiler at high pressure, and that is boiler pressure and superheat temperature, whose enthalpy is already known. After certain expansion, in the turbine from boiler pressure to bleeding pressure, let m kg of steam is bled from turbine at bleeding pressure P2. Hence, remaining 1 minus m kg of steam continues to expand in the turbine isoentropically from bleeding pressure to condenser pressure, that is 2 to 3. Now, this exhaust steam at state 3 enters condenser, where it condenses into saturated liquid by rejecting latent heat of condensation to condenser cooling water. Now the state of the water leaving the condenser is at state 4. This condensate liquid is pumped from condenser pressure Cp to bleeding pressure in 4 to 5 process, isoentropic pumping, and then the water enters feed water heater. Now let us indicate the feed water heater. This is 1 minus m kg of water at state 5, and from the other side it is bled steam at enthalpy H2, that is m kg. So what is leaving there? 1 kg of saturated liquid at bleeding pressure. Please note that the mixing occurs at constant pressure, that is at bleeding pressure. So mass balance is satisfied. 1 minus m plus m kg is equal to 1 kg. The rate of mass of water entering the feed water heater is equal to the rate of mass of water leaving the feed water. That is 1 minus m plus m kg is equal to 1 kg. From energy balance, equation for feed water heater. One minus m into H5 plus m into H2 is equal to the total enthalpy of contents entering the feed water is equal to the enthalpy of water leaving the feed water heater. That is 1 kg is leaving, that is at bleeding pressure, that will be H6, saturated liquid at H6, so many kilojoule per kg. Here, neglecting pump work because it is very small, H5 can be taken as H4. What is H4? HF at condenser pressure. What is H6? This is HF at bleeding pressure. Both these enthalpies can be obtained from the steam tables. HF and HF at condenser pressure and HF at bleeding pressure, that is H4 and H6, could be comfortably obtained from the steam tables. Therefore, I can write 1 minus m into H4 plus m into H2 is equal to H6. That is H4 minus m into H4 plus m into H2 is equal to H6. Therefore, m can be calculated as H6 minus H4 divided by H2 minus H4. This is mass of steam bled per 1 kg of steam entering turbine. So, the mass of steam bled from turbine per 1 kg of steam entering turbine from boiler is calculated. Having known H4, H2 and H6. H2, out of these three enthalpies, H4 and H6 are directly read from the stream tables because they are simply liquid enthalpies, that is HF values at bleeding pressure and condenser pressure. But H2 must be calculated from S1 is equal to S2 equation, equating the entropies at 1 and 2, and then obtain the dryness fraction after obtaining, that is after obtaining dryness fraction of steam at X2, we can calculate the H2. Having known H2, H4, H6, the mass of steam bled is calculated. Then thermal efficiency of the regenerative Rankine cycle is given as H1 minus H2 that is 1 kg is expanding plus 1 minus m into H2 minus H3, that is the total work output from the turbine, divided by heat supplied in the boiler. Heat is supplied in the boiler from 1 to 7, but H7 can be as almost equal to H6 since 6 to 7 is pumping of water where work is negligible. Therefore, heat supplied in the boiler is H1 minus H6. That is how the Rankine thermal efficiency of the regenerative Rankine cycle is obtained. H1 minus H2. Before bleeding, what is the work done? After bleeding, the work done in the turbine is 1 minus m into H2 minus H3 divided by H1 minus H6. The regeneration in a Rankine cycle increases thermal efficiency of a Rankine cycle. In fact, regeneration, a main objective is to increase the thermal efficiency. In fact, there may be a slight decrease in work output because after steam is bled from the turbine, the work done per kg of steam might reduce slightly. But this is not a problem because there is a much more greater decrease in the external heat supplied in the boiler. Because without regeneration, the amount of heat that has to be supplied is between 5 and 1. With regeneration, the heat supplied in the boiler is between 7 and 1. There is a considerable reduction in the heat supplied per kg of steam in the boiler. There is considerable decrease in the external heat supplied in the boiler per kg of steam. Therefore, thermal efficiency considerably increases because of regeneration. That is the bottom line. In fact, the basic use of regeneration is to increase the thermal efficiency of the cycle. Now, let us do an objective question given in GATE 1997 regarding regeneration. Consider an actual regenerative Rankine cycle with one open feed water heater. For each kg of steam entering turbine, if m kg steam with a specific enthalpy of H1 is bled from the turbine and the specific enthalpy of liquid water entering the heater is H2, then H3, that is specific enthalpy of saturated liquid leaving heater is equal to the options to this problem, the above regeneration problem, is given as A, mH1 minus H2 minus H1, B H1 minus M into H2 minus H1, C D MH2 minus H2 minus H1. The solution to this problem could be given as, if you just draw a small figure for feed water heater, mkg is a blood stream at enthalpy of H1 coming from the turbine and entering the feed water heater. There is specific enthalpy of liquid water is entering with an enthalpy of H2 kilojoule per kg. Obviously this mass will be 1 minus m. The leaving mass will be leaving the turbine will be 1 minus m plus m. It will be 1 kg of saturated liquid at H3. So problem is, what is H3? Question is, what is H3? Writing energy balance, m into H1 plus 1 minus m into H2 is equal to 1 into H3. Therefore H3 is equal to mH1 plus H2 minus mH2, that is H2 minus m into H2 minus H1. Answer is C. Now let us solve a problem, objective question given in GATE 2006. Objective question: determine the correctness or otherwise of the following assertion, that is A, and the reason denoted as R. The assertion is given like this: in a power plant, working on a Rankine cycle, the regenerative feed water heating improves the efficiency of the steam turbine. Reason R: the regenerative feed water heating raises the average temperature of heat addition in the Rankine cycle. A, the options are given like this: both A and R are true, and or is the correct reason for assertion A. The option B, both A for assertion and R for reason are true, but the reason R is not correct reason for assertion A. C, both A and R are false. D, A is false but R is true. Looking at the assertion, in a steam power plant working on a Rankine cycle, the regenerative feed water heating improves the efficiency of the steam turbine. Assertion is absolutely correct. In fact, in any cycle, regeneration is basically meant for increasing the thermal efficiency. So, assertion is true. Coming to the reason R, the regenerative feed water heating raises the average temperature of heat addition in the Rankine cycle. This is also true statement, correct statement, and reason R is the correct explanation for the assertion A, because as regeneration is provided, the temperature of the water entering the boiler would increase because of the regeneration provided in the Rankine cycle. So, as the temperature of the feed water entering the boiler for heat supply is increasing, the mean temperature of heat addition, the average temperature of heat addition in the cycle also would increase. Therefore, both A and R are true, and R is the correct reason for A. The answer is option A. Now coming to another objective question of GATE 2006. Determine the correctness or otherwise of the following assertion A and the reason denoted as R. The assertion A is given as condenser is an essential equipment in a steam power plant. Reason R, for the same mass flow rate and the same pressure rise, for the same mass flow rate and for the same pressure rise, a water pump requires substantially less power than a steam compressor. The option A, both assertion and reason R are true, and R is the correct reason for assertion A. Option B, both A and R, but that is assertion and reason, are true, but R is not the correct reason for assertion. C, assertion is true and reason is false. Option D, assertion is false, but reason is true. Looking at the assertion A, the condenser is an essential equipment in a steam power plant. That is absolutely correct, true. Reason R, for the same mass flow rate and the same pressure rise, a water pump requires substantially less power than a steam compressor. That is also correct, because if you look at the steam compressor, the steam is an compressible fluid, because steam is considered to be a mixture of liquid and vapor, wet steam. So when we are compressing the steam suffers a change in the specific volume of the fluid, which requires greater work to be done on the steam compressor. Whereas if you pump the water, which is an incompressible fluid, its specific volume is practically a constant and is of very low value, that is of 0.001 meter cube per kg. So for the same pressure rise, when water is being pumped, it requires far lesser work input as compared to the steam compression for the same pressure rise, because water suffers no change in specific volume. Moreover, specific volume of water is also very lesser, 0.001 meter cube per kg. So the reason R is also true. Reason R is the correct explanation for the assertion A. The answer is option A. Now, looking at another objective question of GATE 2006. Given below is an extract from steam tables. The table is given like this. The saturation temperature, first column in degrees centigrade, saturation pressure in bar, the second column, specific volume, the third and fourth columns are for specific volume in meter cube per kg, which is given as first column is saturated liquid, that is VF, and the second column is saturated vapor. Looking at the last two columns, which is given as specific enthalpy in kilojoule per kg, saturated liquid, that is maybe taken as HF, and last is saturated vapor, which is denoted as Hg usually. So the saturation temperature is 45 degrees centigrade. The corresponding saturation pressure is 0.09593. Specific volume of the liquid is 0.00101. Specific volume of saturated vapor is 15.26. then specific enthalpy is 188.45. The specific enthalpy of saturated vapor is 2394.8 kilojoule per kg. Then the saturation temperature is given as 342.24 degrees Celsius. The saturation pressure is 150 bar. The saturated liquid have the enthalpy of specific volume of 0.00165, and saturated vapor has specific volume of 0.01033. Saturated liquid has got enthalpy of 1610.5. Saturated vapor is having an enthalpy of 2610.5 kilojoule per kg. Under such conditions, given this table, the specific enthalpy of water in kilojoule per kg at 150 bar and 45 degrees centigrade is A, 203.6 kilojoule per kg, B, 200.53 kilojoule per kg, C, 196.38 kilojoule per kg, D, 188.45 kilojoule per kg. The answer to this question could be given as long as the water is in the liquid condition, as long as water is in a liquid condition, no vapor is there, its saturated liquid enthalpy is always given by its temperature in degrees centigrade into 4.187 kilojoule per kg. Therefore, HF at 45 degrees centigrade is 45 into 4.187 kilojoule per kg. The answer should be close to D, that is 188.45. In the table also, if you look at the saturation temperature corresponding to 45 degrees, saturated liquid enthalpy corresponding to 45 degrees centigrade saturation temperature is 188.45. And if you multiply second row, that is saturation temperature corresponding to 342.24, that into 4.187, that should be 1610.5 kilojoule per kg. So the saturated liquid enthalpy of water at 45 degrees centigrade is 188.45 kilojoule per kg. That's the answer. Answer is D. Consider another objective question given in GATE 1995. Consider a Rankine cycle with superheat. If the maximum pressure in the cycle is increased without changing the maximum temperature, and the minimum pressure, the dryness fraction of steam, that is quality of steam, which can be otherwise taken as after the isoentropic expansion will increase. State whether above statement is true or false. Now let us draw the given statement on a TS plane. We had considered the Rankine cycle with a superheat, that is 1, 2, 3, 4. If the maximum pressure in the cycle is increased, that is boiler pressure is increased without changing the maximum temperature. The maximum temperature is kept constant. So we have employed higher boiler pressures. The dryness fraction of steam after isoentropic expansion will increase or decrease, is it asking the question. In fact, the dryness fraction will decrease. X2 dash is lesser than X2. The statement is false, because when higher boiler pressures are employed without changing the condensing pressure or minimum pressure of the cycle, the dryness fraction shall decrease.